Hi, I'm Sven. I am a mathematician I did my PhD at Johns Hopkins in algebraic topology, and then wandered into security by accident during my postdoc in machine learning, geometry and machine learning. And now in my postdoc, I founded AI Village like 8 years ago. And a lot of stuff has happened since then. But one of the things that sort of irritates me about a lot of the conversation around AI is that people forget that it's been going on for a long time, and there's best practices that people have been doing for 20 years now. And there are very good reasons why these best practices aren't well known, and they're kind of siloed in each organization, and those silos don't talk to each other that much. There was a bunch of conferences and spam back in the early, about 2004. Then they solved spam, and no one's talked about like a lot of the AI security principles since then, because like Google figured it out, Facebook figured it out. Then my friend at Quora started the spam program there, and she had to figure it out on her own and just like rammed her head against a wall repeatedly, but over the course of 2 years figured it out. And that's basically the story of a lot of AI security for the last 20 years. So I'm going to talk about why and some of the examples and stuff here. And hopefully, by the end of this, you'll understand there's things to learn. And the thing I was doing at Singapore was trying to set up a way to teach people how this stuff works. So the first reported vulnerability in a production machine learning model is from 2004. It predates that, but the Usenet post that I had from 2003 got deleted. But I have a citation for 2004 from John Cumming-Graham's blog post that he reposted in 2023, because I've been talking about it so much that reporters came and asked him about it. And the first reported AI vulnerability was Bayesian poisoning. So you have the spammy link that you have at the top that you want everyone to click on, and it gets clearly notified as spam by a naive Bayesian classifier. So what you do is you can take advantage of the mathematics of that classifier, just add a bunch of hammy words, and the most hammy words you can, to undo the spamminess, and then it gets classified as benign. This was one of the 7 bypasses for spam detectors that John Graham Cummings was producing back in 2004 with the pop file thing that you might remember. I was 16 at the time and had no interest in spam, but it's been around for, this was they had a lot of conferences where they were talking about how to solve this problem. And one of the things is there were 7 bypasses that were discovered within the first few months of a spam detector being deployed, a naive classifier being deployed to do spam detection. And this is the first learning that you have to have. There's always other bypasses, and it goes beyond normal security practices of you're never going to catch all the vulnerabilities in a piece of code before you release it. You're never going to think it goes past that. You should just not even try at some point, because models make mistakes. A model without any mistakes is the holy grail of data science. You've got a transformer that never makes a hallucination. You have artificial general intelligence, probably. I don't know. It's far smarter than us, because even we hallucinate. Production malware models are at least 4 nines accuracy, preferably 5 or 6 nines of accuracy before we can release it to our customers. I worked at Endgame for 4 years, where we managed, and I managed the malware pipeline there. The false positives are at most 0.01%, and the false negatives are that similar on release, and we still, at those rates, consider this to be insecure in a matter of time before someone starts taking advantage of our mistakes. Because That's what attackers do. Every time they make a mistake, it's just a matter of time before they find it and start executing on it. And there's nothing machine learning models can do to stop that. And anybody who tries to tell you otherwise is selling you something. One of the big things is out of distribution data. So this is the simplest example that I can come up with. Imagine building a model to do MNIST, which is the text digits. This is like the proof of the simplest test you can get. If you have a machine learning model, you run it on MNIST, and if it does well, you've got something promising. It's like the unit test of data science. Someone released fashion MNIST. The inputs are identical. It's a 28 by 28 grayscale image that, but trained on MNIST, it doesn't do what you want to do. It's going to predict like the shoe is 0, and there's nothing, like you can't train the model to say, I don't. And this is one of the things that people have tried to do for years, and it doesn't quite work. Because that's like the big thing, like that distribution of the fashion MNIST is very much distribution with the standard MNIST. But with PE data, stuff that's released 2-3 months, like PE data, like benign-ware and malware released months after I've frozen and trained a model on up to a certain amount of data, is already out of distribution with the data, the data. And it can be significantly out of distribution. The source of error that I cannot control. I don't even know what my error rate is on that out of distribution data because I couldn't even test on that because I've only got the data that I have at release. I can't test on future data because I can't make it. And there will be somebody, the models memorize and interpolate the data and they don't generalize. And attackers always do weird things to get around controls all the time. They always go out of distribution. They always do weird stuff. So combined with the fact that you make mistakes, so they could exploit something that's in distribution, and they could exploit something that's out of distribution, you're just like hopeless. So for a thought experiment, think about deploying like a simple API, something you can fit in 5,000 lines of C, just like straight C running on the Linux kernel. That's the entire API, and you're running it on one piece of hardware that you control. You choose the hardware. You could theoretically make that secure. Like, if you support over those 5,000 lines of code long enough, you could make that so that that's secure. You could leave it in a corner, and no one's going to pop that machine. No one's going to pop that API. Okay, and we've kind of done this with some of our. Like, when was the last time that like the actual financial in your bank got popped? Like, people have broken in the login things. That there's all sorts of things that go around it, but the actual financial transactions that go on through Wall Street is done to a level where it is pretty much secure, and we trust it. But you should think of AI as more about like you have a enterprise with tens of thousands of endpoints, no clear understanding of what they own. You need a solid EDR, a large SOC, and you're going to get popped. And you're relying on a triage and response team then for your security, more so than like just securing your systems. AI is like the next step. Like, don't even pay for someone to build a firewall around your system. Just pay for a better and better triage and response. This is a 2D slice of a 780 dimensional data set. It is each color in this image is a unique decision path that MNIST model can make. This particular model had 60 hidden layers, meaning this particular model had at least 2 to the 60 different colored regions in the 780 dimensional space. It has hidden nodes. That means it has the 60 times 800 parameters, and that's it. It's in the order of tens of thousands of parameters. We are talking about we talk these days about ChatGPT, which has got trillions, may have trillions of parameters. And classifier. This is not even a version of the MNIST data model that can work ad production, those have at least 2 to the 500 regions. And we need to check that each of those regions are classifying things correctly. So there's no, and that's the sort of thing, like you've got to go check 2 to the 500 things. And I know there's going to be some mathematicians who disagree with me on this, and I can argue with them about some other time. But it's like that order of problem that we have to solve to make things secure. So just kind of give up hope for securing your model, because just assume someone's going to pop it. All you can do is delay the pop and hope you see it when it comes and respond quickly. And now someone's going to tell me about adversarial training, adversarial detectors, there's layers to make things work. Basically, every single one of these things doesn't work in real life. Go look up the work of Nicholas Carlini. Every time someone's published, I have an adversarial defense that will defend your model perfectly against these types of attacks, Carlini breaks. And he's been doing this wonderfully since 2017. And he's got like, the 10 years of experience breaking defenses against machine learning for defeating machine learning models. So given that like the situation is kind of hopeless, what do you actually do to secure the model? So here's the best quote that I can find on this thing. We measure ourselves on the speed which we can detect and respond to new types of attacks and mitigate the potential damage caused. Facebook spammers ruthlessly exploited their spam detection, their spam models, found bypasses in spam detection, and it was just thousands of people trying this over and over again. And so they're going to get past, and that speed and new type, finding the new types of thing, the speed is the key part in like actually building a proper defense against machine learning model for your machine learning model. This is more about AI security than anything. This happens in malware. This is we trained on January 1st, 2019. We really see the blue line is the false negative. That spike in about April 2019, was basically a bypass. And then if you see the thing going forward in time into the mid-2021, that is another massive bypass for this model. It goes stale at about 3 months after release. So we released once a month to stay ahead of this. We couldn't do the detection response stuff, so we just like iteratively defended the model, kept the model up to date. And now, so how would you do this? So this is the historic strategies to make AI security manageable. So first thing is robust features. This is reduce the amount of information your model sees and make it hard to manipulate. So you make your model hard to manipulate by making the information the model sees hard to manipulate. So for spam, use behavior of people. There's an intrinsic thing of spammers want to send out a lot of links because they have a low rate of click-through. So they want to send out a lot of links. That behavior is intrinsic to how their business model. If you can find that behavior and detect on that, rather than the content that they're doing, so much better for actual detection of spam. And that's how spam works. These spam detectors work these days. Facebook's site integrity team don't even look at the content of what you're posting. They literally just look at the behavior of the user account posting it. For malware, use features that are hard to that change the execution. This is one of those things where it's an active area of research. We want to do dynamic analysis of the models, but we can only really do static analysis because the compute in our laptops isn't quite there to do dynamic analysis. But I'm personally hoping that with some of the newfangled AI chips that are being shipped with laptops, that in 4 or 5 years, we'll have dynamic execution models that can find ransomware far more effectively than any of the static analysis systems that we have today. For LLMs, the behavior of your API key is far more effective at detecting whether you're abusing the system than the actual input. Here's one example. For bad features. So this is Silence, I Kill You from Skylight Cyber. They had, Silence had a machine learning classifier that turned PE data into, is it a good or bad? And this is basically the pipeline. The first function is your featurizer. They featurized way too much. and then they put it into classifier, and whether it was good or bad. One of the problems that they had was Fortnite and Rocket League kept being detected as malicious because Fortnite, these games do kind of funky things to the memory and the RAM, and they have hooks that are not good. So they needed a way of excluding Fortnite and Rocket League from the data, from the model, and the model without changing. And they didn't want to retrain the model because they chose to have a single static model and not redeploy every month. They redeployed on the order of every few years, which is ridiculous. So it's to allow list Rocket League a nice subset of features that included string data, and found that point of Rocket League, the centroid of Rocket League, and allowed everything within the radius of the centroid to just run. And now what people did was they attached the Rocket League strings to malware, and Cylance was just like, yep, it's benign, let it execute, which is exactly the same stuff that happened in 2004 with the Bayesian. And this is because their features had too much information. They need more information than their model needed to do its job. So you want to go for hard features. So spam, like IP address, behavior, domain things. Google is now making all your spam before you send it out. If you are a marketing company, they make you pre-register the actual emails before you send it out. The fact that it has to execute constrains its behavior significantly and has helped. But dynamic behavior is hard. You can talk to me. I'll happily talk to you about how to do dynamic stuff. So a lot of friends are researching that. LLMs, account, and behavior. Next thing, and here's why it's not well known, obscurity is security. So don't talk about what your model is. Just say nothing. Even rejecting the spam or rejecting the malware and not letting it execute is saying something and is giving information. But that's the minimum you have to do. Just say nothing. Example, if you were here at the CTF last night, this is from Will Pearson and Nick Landers. They got the world's first machine learning CVE back in 2019. A Proofpoint responded to a spam email with this in their header information. Each of those highlighted, the bolded numbers are information for different classifiers for how their model worked. And now what Will and Nick did was they built a classifier that imitated that. They just sent a bunch of a data set over to them, got all the data back for how their models worked, and then it imitated their stuff. And like they were giving away way too much information. It's basically giving away the farm. They should just respond with like, it's done. And this is just drop the response if it's spammy. But that's what they responded it with every time. And so they stole it. Good obscurity, I'm not going to tell you who does this, but what they do is so you know how they took a PE sample and turned it into 7,000 dimensional vector for training the model on? In this case, this is a social media site that needed to do similar things, and they had a lot of bots and a lot of people trying to learn their spam algorithm. So they needed to change it up every week. So they had a library of feature extractors, and they would pick a subset of about half of them randomly each week, and then they'd train their classifier on that random subset of their total features. They only used a small portion of the actual features, and they kept changing it. So the spammers wouldn't learn how the algorithm worked, so they couldn't get their feet underneath them. And because as they built up their thing, they came up to a critical mass, and spammers learned the algorithm, they had a good stuff, and they kept going. And then they learned that they could drop half of their features and still have a good classifier. And the other thing, speed is security. You will be breached. Your task is to minimize it. So find it. That's the hardest part, is finding the stuff and blocklist it. And just finding it and blocklisting it is your first task in any sort of AI security. You have to have layered security system. So your initial response is just blocklist it as quickly as possible because that's your triage to get things done. While that's being done, while you're stemming the tide with just like sticking a finger in the dam, build the next model that does classify this correctly, redeploy, and keep going. Layered security, this is how the Sophos malware detection system works. They don't consider it to be a one-off model. It's not check if the PE model detects a file and says yes or no. They have all sorts of different models and systems that help keep you secure, and that layered security is how they do it. There are several block list allow lists in there that help stop things. There are several models in there that help stop things. Some of these can be redeployed and retrained faster than others, but they have a plan for how to do it, and layers of security, and those layers are different levels of agile and different levels of accuracy. But the big thing is like minimize your retraining time. So a lot of companies get into this for the first time. They build a really good model that's really high quality. It takes a week to train. And so what happens is they train it, they deploy it. Someone finds a bypass 7 days later after they train and redeploy it, and then they have to train another one, and they have to spend 7 days training the next one. And those 7 days, they're just getting pwned every single minute of those things. So they just they lose constantly. So if you don't have a really fast retraining time, you will lose. So you need to get, so one of the things I did at Endgame was I got our retraining and redeployment time. Remember, we deployed once a month because malware is much, much slower than spam. So we had it at about a week for retraining and redeploying, and I got it down to 24 hours. And that was like a lot of work. But the biggest thing is detecting a breach. If you have a billion queries a day, like CrowdStrike says they have for malware, finding the new strains of malware in those billion queries is very hard. It's basically impossible. It's looking for a needle in the haystack where there's far more hay and you don't have a magnet. So billions of new posts a day, maybe millions of which are spam. Billions of PE files a day, maybe a few thousand of which are new malware. Hundreds of thousands of new strains of new files a day. So like it's a needle in a very large pace. Here's where things, the emphasis on like response time and minimizing things really comes into effect. Mature companies spend far more on detection of new types of attacks and like monitoring the models than actual model development. You get to a point with the model development where it's good enough and you just try to maintain that thing, which I'll go into more detail in a bit. But last thing is learn from the attackers. In an adversarial machine learning system, your attackers are far more innovative than your small red team. Spam, they sell techniques to each other. So one attacker doing something sells it to another team. And you should figure out what that is and defend from it as quickly as possible. Malware reverse engineer the strains that you persistently miss. There might be a new feature that you can add to your malware classifier that allows you to do this. LLMs, they make up jailbreaks on Discord servers. You can join those servers too and just watch them do it. And you've also, there's all sorts of things you can do. One of the things that you might not be aware of is the search engine optimization people are red teaming the Google search engine, which is an AI model that's been around since 1999. They have conferences on how to manipulate the Google search algorithm. They read papers and books. They read every time Google releases a paper on how their search engine works, they read them, come up with theories, and then test them against Google. And if they do this in the open, you can go sign up for their conferences and learn how persistent 20-year-old AI red teamers work. One of the examples that you come up with, and a lot of people talk about this, and this is particularly irritating, is adversarial examples. This is the panda nematode gibbon thing, panda gibbon. This is from one of the first papers on adversarial machine learning. As a mathematician, I am absolutely fascinated this. As a security expert who's worked on securing a malware model, I do not care. And the reason why is if you have two options. One, adversarial example, delicate, tricky math to get working. Oftentimes you need access beyond normal, far beyond normal access to the model to get this working. It doesn't really work for spam or malware because the way those classified, you have to go through a featureizer first, and that featureizer drops a lot of information. And needs a really good understanding of malware. So like if you've got someone who can build a system to build adversarial examples for malware, that person is extremely valuable and is probably not going to be making malware for long. Option B was in the cloud. There's already thousands of people building stuff and communicating for malware and spam. Like they can just tell each other this worked and got past you. And they get to know the algorithm a little bit, which is why you need to keep things quiet and cheap and easy to distribute. If you had the choice when you're running a business for malware class for adversary, an adversarial business like the criminals, which would you choose? But keep in mind, they do read the Ember 2018 paper that released an open source malware data set. They read that and they changed the way they wrote malware based on that paper. So it's mostly B with a little bit of A. One of the things that people talk about, and you're going to hear over and over again if you go in the space, is model poisoning. You inject a small amount of data in a model to change its behavioral in a desirable way, and it's tiny fractions, 0.1, 0.01% of the data set. How are they getting the data in? How much? Why? If you're actually securing a model, like this is your data set is the crown jewels. How you ingest data is something you pay a lot of attention to. And if you want to poison VirusTotal, you have a system where you've got a torrent of data. Malware EDR vendors save a tiny fraction of the total data set traffic that we see. Spam, tiny fraction of the total traffic of Facebook goes into actually training the models. You deduplicate that thing. A lot of the poisoning techniques just collapse in the volumes that we have to deal with for actual production models for securing systems. And your poisoning attack needs to survive this. If you actually wanted to poison VirusTotal and execute on that, you'd have to upload hundreds of thousands of samples a year to do that. And someone's going to notice. So to give a summary of sort of things, the recap diagram for executive, this is the Gartner dartboard. So there's kind of three axes of AI security. Attack quantity, how many people are trying to get past that model and how valuable it is to get past that model. So Facebook spam model is extremely valuable. Gmail spam models probably is less valuable because of the way the world operates these days. Email spam is not as valuable as social media spam. The way you reduce this is you have verified accounts, API limits being less popular, and like if you went to your CEO and told us like we need to secure the model, and so we need to sell less, they're probably going to laugh you out of the room, so you can't do that. But like verified accounts, API limits, just refusing to respond to more than a few thousand requests per minute or requests per day, helps you reduce the amount of information you're giving to attackers. And then the other axis that you have is the attacker control. How much control do they have over the system? The more outside of the thing they are, the harder it is. So you want harder to manipulate features, less public information, and a moving target. And you kind of get these contour lines. So you want to be, on the 1 year level of redeployments, not the 1 week level of redeployments. And if you put, kids with the darts come in, you have self-driving cars, which are very much not a security problem. What's the incentive there? How many people are actually attacking that system? There's so many more ways to like break self-driving cars than like adversarial machine learning. And half the attacks that people talk about require like access that are far beyond, like if you have that access, there's other things you do to the car, like just slam on the brakes or like accelerate to 80 miles per hour rather than do some weird adversarial machine learning attack that causes it to slam on your brakes or accelerate you to 80 miles an hour. Malware models are about the 1 month deployment. The attackers have a lot of control, but there's not that many attackers doing this. Modern spam, it's like crazy towns over there, but attackers have very little control because there's so many people going after it that they can figure out ways past things. Cylance, they screwed up. And this is really the core of why they screwed up. It wasn't so much that they built something, they just gave the attackers more control than they needed to. That's the core of the vulnerability that they had. With Proofpoint, it's a similar thing. They gave the attackers too much information so that they had more control than they needed to. And that's really it. Like they didn't find a vulnerability that is like classic vulnerability. They just gave it more information, more control than they needed. Prompt injections, probably down there. The problem with prompt injections is there's just the incentive to get past that stuff isn't that great. Like how many actual systems security rely on prompt injections? Like it's really funny on Twitter to break a bot and get it to write a haiku suddenly. But like there's not much money behind the stuff, and I don't think I'll happily argue with people about this, but I think it's not that serious a problem. The summary of basically mature teams can't control how popular the service. Better features are too expensive or impossible. At some point, you've got the best thing you can do. So they focus on the response time, finding things faster, patching the problem, and redeploying. I've only got a few minutes left, so I'm going to focus on questions. Anybody, rather than talking about like the other axis, which is like weird stuff your model can do. But leaving on this, any questions you guys have?
This OpenPM source of information. Want to learn more.
Can you
yeah, so the question was, what would be a good source for people to learn more about the stuff I was talking about today? Honestly, it's like talk to people who have done it. Like that's it. Like that's really what you have to do now. I announced at DEFCON we're doing this thing called the AI Cyber League, where we're going to be teaching college students how to do this by making them defend a LLM they have to build their own guardrail system. So they have to learn how to build learn how to build an observability platform, a whitelist, allowlist, blocklist system, and then the guardrail system, and they have to like keep those up to date and train them. And we're doing that all in the public, and because it's for students and stuff, like we can do that all openly. And I'm working with like friends of mine at Google and NVIDIA and places to like build that thing. And I'm hoping that just the blog posts and the tutorials and stuff from that are a good resource. But that's going to be starting in January 2025.
I have another question over here.
Yes, hi, great presentation. What would you say is the state of AI defense, and what measures should we be thinking about that are more advanced than what the adversaries are currently using?
So are you talking about defending the machine learning model itself? Or?
Well, defending the model, defending the AI infrastructure, architecture, all of the above?
So like AI security is at like the very top of your Maslow hierarchy of needs. Making the worst AI incidents that are out there are like someone left an unsecure S3 bucket and we messed with their data set. And that's honestly like the worst instance that are out there. And it's just that basic security. But like once you've sort of got the basics done, it really is like how little information can I give this model and how much it's like what I like this, just making sure that you have robust features, other things. Like the other sides of defending machine learning models, like I'm going to defend against like this adversarial example system. Like it doesn't, like, unless you've seen it, don't care about it. Like unless you've seen like a lot of people doing it, just don't buy that product.
All right. One last question, and this question I'll put in. There's several questions in the Slack channel. When you get off the stage, you might jump in there and also take a look at it. So Sven, you mentioned and emphasized the importance of minimizing retraining time for AI security models in order to stay ahead of the attackers. Can you provide some specific strategies or techniques used to dramatically reduce the model retraining cycle? What were some of the key challenges you had to overcome to achieve those fast retraining times, and how can others in the industry adopt similar approaches?
When you're doing like large model training, the pipeline of extract, transform, and load to get the model out, the data out of the format that you have, like, you know, you're going to have like an S3 bucket filled with samples or like a database filled with samples. You need to take that and transform it into your actual model, the inputs to your model. Caching those responses is one of the things I did, which was the main thing that we did to get it down to one day. Using like actually scalable things, like I know people like using Spark, but I found that Spark just doesn't go as fast as just a pile of Docker containers launched on AWS. If you can, there's like the good data scientists spending time on reducing training time is the main thing. Like the actual specifics come down to how your model works. Like you on GCP using BigQuery, that's one whole pile of solutions there. You know, AWS using Spark, there's a whole different pile of solutions there. Like how are you actually training the model? Like caching is the one thing that's kind of universal. Can you like pre-compute things during the week while you're like running up to maybe a retrain, so that you can just like hot reload? Fine-tuning your model if you can. A lot of companies did that. They fine-tune the model every so often, and then they do a big retrain every rarely, because the big retrain took like a week, but fine-tuning can take as little as a few hours. But it really depends on how your model works.
All right. So big round of applause for Sven. Thank you so much for sharing your insights.